and is working on computational fluid dynamics, unsteady aerodynamics, as well as data science and fluid control theory. So today he's going to talk about network-theoretic analysis and control of unsteady fluid flows, where he will discuss some challenges and successes in applying such network formalism for fluid dynamics. So I would like to remind everyone that this talk is going to be recorded. So if you are not willing to show yourself, just turn off your webcam. And at the end of the talk, we'll have about, let's say, 10 to 15 minutes for question time. And so I think we are ready. So dear Aditya, the floor is yours.
Thanks a lot for the kind introduction, Giovanni. I really appreciate the invite. And to everyone who has joined the seminar series today, thank you for showing up. I appreciate that during this difficult time, you guys are showing up for research and conferences and all of that. So really appreciate you showing up. Good morning, good afternoon, good evening, wherever you are. Hope I can make your time, your next at least 45 minutes worth it. And hopefully you can learn something about networks, and maybe I can learn something from you with your questions afterwards. So today's topic is going to be about network theoretic analysis and control of unsteady fluid flows. And I like to joke around that the beginning of this started with my advisor, Kunihiko Samtaira, listening to the NPR radio. And when he was listening, he basically said, hey, there's some cool graph theory stuff going on. And they were talking about it on the NPR radio. Aditya, why don't you go and look at this, cute little, fun little side project? And, I was hired to work on something else, more computational, but this turned out to be my dissertation and focus area. So just an interesting anecdote. So just to start from a big picture perspective as to understanding some of the challenges in fluid dynamics, I'm interested in two of them. Of course, there are many. Is that one of it is modeling the multi-scale and the nonlinear as well as unsteady dynamics in unsteady fluid flows. And here, the main concern is that the interactions between fluid flows or things in fluid flows or objects are not very easily interpretable. So that is one. And the second one, the challenge that I'm really interested in is that closed loop feedback control to do active control to optimize engineering systems, is again a very, very hard problem, particularly because the design space in unsteady fluid flows, because of its high dimensionality, is too large to deal with. So these are kind of the fundamental questions that we started to think about, and we were like, okay, can network theory and graph theory help? So again, three motivating questions that I hope to use network theory and data science and all of these cool modern technology now is that the first question is, can we construct parsimonious and interpretable models? And what I mean by that is, you want models that have an inherent sparsity. So we already, I think in this community, we are aware that, sparse models have inherent robustness to them. They have, they're easily interpretable because, you don't have these dense network of interactions. So can we reveal, first of all, the underlying network structure and then comment on, can we construct, say, sparse or interpretable models? And that's where I feel like at least network science and graph theory really shines, because once you can design a network or a graph, then the representation of a complex phenomenon or any system that you care about becomes really simple and elegant. And that's where we want to go. And the second question that we asked is, there's also, a big push in fluid dynamics to basically understand coherent structures, the big structures, modal structures in fluid flows. But the fundamental question remains that how do these modal structures exchange energies between each other? So if you have a gazillion modes in your system, you want to really understand how these modes interact with each other in some meaningful way to basically comment on the flow behavior. And the third question that we wanted to ask is, sure, you're talking about models that, if you have full flow field information, you can give me some insight on the model as well as the control strategy. But what about like if I can't measure everything in the flow? What about if I can only measure a few quantities in the flow? Say you have some sensors and you have some data that you can collect from these sensors. Can you then design some control laws or control strategies using some data-based network science-based approach? So these are kind of my kind of motivating questions, if you may. But again, like to answer these questions, there's an array of tools out there. One tool that was getting really popular by the time I started my PhD was this world of network science and data science. So I would say it's a very, very exciting time to explore these ideas in the fields of network science and data science. And hopefully this presentation can motivate you in that direction somewhat. So this is just showing you a collection of areas that network science and data science have, of course, shined in, which is in understanding functional as well as structural networks in the brain. So a collection of neurons and how they interact with each other. Genetic networks. In epidemiology, we live in a world where we really, really need to understand spread of infections, viruses, diseases. So it's really important, and study of network theory is really important. Social networks, of course, we're all on social media. We're always connected to each other, so network science plays a big role. And there are, of course, the machine learning, the artificial neural nets that are kind of coming out from that network science methodology. So there's tremendous potential for integration of these tools with fluid mechanics. Especially, like I said before, my interest is going to be in building interpretable models as well as designing control laws. So by control laws, I mean you want to do some control of the system to improve on some performance objectives. Okay, so let's start with the basics. I know some of you might be familiar with networks, but I like to have this slide just to get everybody on the same page. Is what is a network? A network is a really simple thing. First of all, network science examines interactions and evolutions between interconnected objects in the system, whatever that might be. A network is basically defined out of three quantities. The first one is nodes or vertices. So if you can define vertices or nodes in your system, you already have started a network or a graph theoretic representation. The next is edges. So if you have a collection of nodes, they are connected to each other. For example, say I'm a node. Giovanni is a node, I'm connected to Giovanni, and I have an edge between me and Giovanni. So basically, the interactions between me and, for example, Giovanni is described by that edge. Now, how connected am I is described by the weight of that edge. So that is a pretty simple representation of what a network is. You have nodes, you have edges, and you have some weights describing the interactions between the objects that you care about in your system. So if you want to compile this representation in terms of a matrix, the most important matrix that you need in graph theory is this matrix called as the adjacency matrix. And as you can expect, all that matrix is saying is it's a collection of weights. So if I have an edge between I and j, that is represented by this wij. If there is an edge, if there is no edge, if there is no connection, then that edge weight is just going to be 0, basically. And the second most important metric in graph theory is the graph Laplacian, or the discrete graph Laplacian. Now this might be familiar in the sense that this is the discrete analog of the continuous Laplacian operator that we are familiar with in fluid mechanics. So here you can see all that it entails is you have this DG matrix, which is basically just a collection of the node strengths. For example, if I add all of my connections up, that matrix, that strength is represented in this really nice diagonal node strength matrix. And of course, A again is your adjacency matrix. So it's a very simple representation of what a graph is, a collection of vertices, edges, and edge weights. So can we use a simple looking framework to analyze unsteady fluid flow interactions? And that's where we started our journey from. Now, I'm going to give you, now, of course, you can say there can be multiple ways that you can construct a network or a graph. And you're absolutely right. There is no one, it's not a one-stop shop. It is almost, I would say, a design problem in some sense. You need to design what your nodes are. And what I mean by design is, say you care about certain quantities in the flow, those could become your fundamental nodes in your network. So in my case, I was interested in, like I said, the motivating questions before, I was interested in building sparse interaction models in these fluid flows. And the most fundamental element that you can get in fluid mechanics is vortices. So I started with thinking about these nodes as vortices and edge weights as you will see in a bit what the definition of the edge weights is. But physics already gives us what the edge weight should be between vortices. And what that edge weight is essentially is just the induced velocity between the vortices. So this comes from the Biot-Savat's law. I will just describe that in detail in a bit. But essentially, the answers are all out there. It's just putting it in this framework of networks and using all the tools and all the methods that come with it to build these parsimonious and interpretable models. The second one, of course, we're going to be talking about is turbulence network. I am really interested in thinking about turbulence, all of the interactions in turbulence, and it's such a rich and challenging problem to understand turbulence. So I feel like there's a lot of scope for applying these database tools. And I'm again going to show you a demonstration of how we used this network theory and graph theory in the context of turbulence. And then I'm going to go into analyzing interactions between coherent structures or your big dynamical structures in the flow, where again the nodes are going to be the modes of the flow. A bit of a rhyme there, but it's in some sense we want to understand what is the interactions between these modes in the flow. So those are going to be my nodes of the network, and I'm going to be interested in characterizing what the energy transfer is between these modes. So like you can see, the way I'm building these network models and network problems is first by positing, what do I want to describe the interactions between? And once I know that, what is the end result in terms of, the interaction? For example, if I'm describing induced velocity or if I'm describing energy transfer, that can be described in a network. And finally, I'm going to be talking about this idea of transition network. This has a lot of flavors with what Giovanni has given a talk before. This has a lot of flavors on using time series data to build network-based representation. So there are some ideas of overlap there, where basically my nodes are going to be cluster states of my system, and the edge weights are going to be the probability of transition between these states. So these are what we call as transition networks, and I'm going to be walking you through these 4 kinds of networks for answering those 3 fundamental questions that I talked about earlier. So the first I'm going to be talking about this vertical network, and I just summarized the paper below. You can go and see more details on the implementation. So again, starting with the first question, can we construct simple, interpretable, and parsimonious models? So we start with building vertical interactions in fluid flows. Now, the beauty about fluid flows is that from theory, we know Navier-Stokes equations, if you put an inviscid approximation on it, you can distill it down all the way to a simple ODE describing the behavior of discrete point vortices, of which all of the vortex methods are based on. So what that tells you is, if I'm a vortex I and there's another vortex j, I induce some velocity from I to j, and that has a very, very simple form, which is if your interaction from u, I to j. So if I'm a node I and then I'm basically interacting with node j. Basically, all that is in 2D, it's dependent on the strength of I, which is kappa I, or the circulation, basically, of me. And basically, the denominator you'll see in 2D is Ri minus Rj. So Ri minus Rj is just the distance between us. So as you can see, in 2D, essentially, the interaction is just kappa I, which is the strength of this of me, and then the distance between these vortices. So what that means is that if I have a higher strength, of course, I influence the other vortex in the system in a larger capacity. And if, of course, you're closer to me, I again interact with you in a meaningful way, which is basically I have a high level of interaction between you. And of course, if you're further apart, or if my strength is really small, I don't impose that much interaction over you. And this definition can be extended to 3D, basically. I'm just showing you a schematic of what that definition in 3D looks like. And of course, you can describe this in what we do in essentially representing vortex dynamics or vertical interactions, is use this precise definition as our edge weights of the graph. So this, this Wij is basically given by the interaction from I to j and from the interactions from j to I, which is basically the j to I is incoming interactions and I to j is just outgoing interactions. That's about it. So this kind of, once I define the weights of the graph, you kind of, know a lot about how to represent this problem. Okay, great. So we represented, fluid dynamics problem, or these vortices, and describe their behavior in terms of a complete graph, which is I and j. And of course, you can see by the definition, this is going to be a complete graph in some sense. And that's why fluid mechanics is so rich, is because, you have these interactions that every vortex influences every other vortex in the system, basically. So if that is the case, you get this complete graph representation. Now you can see on the left that I show you, this is the complete graph, and this is the corresponding adjacency matrix. Now, there is no particular reason why I aggregated them into communities. This is just to show you for graphical clarity. But you could basically have this system any way you want. You can have this vortex distribution any way you want in the system, and you can still apply all of these methodologies that I'm going to be describing. Now, what we borrowed is to develop these parsimonious and sparse representations is we borrowed an algorithm, which is a really, really beautiful algorithm from Spielman and Srivastava. And it's called as graph sparsification using effective resistance. So the idea is basically you built this metric called as effective resistance once you have a graph, and then you use random sampling procedure to build spectrally similar sparse graphs. Now, what do you mean by spectrally similar? Is if my graph is AX is equal to B and A is your adjacency matrix, then the sparse graph that you get has the same eigenvalues and the same eigenvectors as your original adjacency matrix. Now, this is beautiful. So even when you're cutting the interactions, you're not cutting it randomly. Of course, you're using random sampling, but weighted with this the probabilities of the random sampling are proportional to the effective resistance of this entire circuit. And if you do that, what happens is the weights are getting redistributed. So if I have some interactions, and if I cut my interactions, for example, if I cut my interactions with Giovanni, I really have to compensate in some sense, in terms of, getting the same dynamics and, living life the same way. Exaggerated example, but in some sense I have to compensate for that by adding weights somewhere else so that my dynamics is very similar. And that's exactly what the spectrally sparse graphs do. So you can see a lot of the edges that get cut is in these blue regions, but when you're cutting these ties, which can accumulate very quickly, you compensate by having these denser ties getting more dense in some sense, or adding more weights to those closer interactions, if you may. So you can build really, really sparse graphs from using this technique. And what we do is essentially to build fast models of vortex dynamics, and you can incorporate this into vortex methods, and that is an avenue that hasn't fully been explored yet. This is just a demonstration that this can be used, but this can be used to build really, really fast vortex methods. Now, the most classic vortex methods that we all know of is the fast multi-pole summation, right? It's really fast. This, I would say, is kind of in the same vein, but using a totally different technique, right? You just prescribe the graph, you sparsify the graph, and you stick it in. That's it. There's no box construction. There's nothing of that order. Just a dense graph and a sparse graph out. Use that as a preconditioner. So you can see here, all I use is when instead of summing over all of the weights, now I just sum over the sparse weights. And essentially using this in this way, you can build a really sparse model, and you can track the bulk motion of these clusters really, really well. And I show some scaling properties in the paper and all of that. And as you can imagine, as you keep going in time, you need to re-sparsify, because the graph weights are dependent on the distance between us, right? So if I have a vortex strength, of course, in this Biot-Savart setup, the vortex strength doesn't change, but the position between the vortices change. So you need to update that position and do resparsification. And what we show in the paper, that even doing resparsification is much cheaper than doing the full order model. So you get really good n log n type scaling in terms of the reduction of these vortex methods. Great. So just to give you kind of perspective on what is the difference between these reduced order models and what you built. So basically, reduced order models reduce the rank of the system. The sparsified dynamics model that I presented cut ties between these vertices. So it's not essentially reducing the rank, but it's reducing the number of interactions and hence the complexity of the system, right? So the sparsity is helping in terms of cutting ties or interactions. So it's a different perspective to thinking about reducing the model order complexity, if you may. Now you can basically use the benefits of both ROMs as well as sparsified dynamics models by building community-based models, basically. And what that means is you can, again, build the graph exactly the way I told you using this induced velocity, but now use another tool from network theory, which is of modularity maximization. The modularity maximization, what it does, it builds community structures. It identifies community structures in your flow problems. Now, I'm going to nicely direct you to my colleague's work on this, which is Murli. He's done some beautiful work on using communities in terms of leveraging this idea of networks, and then building these networks in laminar flows as well as turbulent flows. And once we can built these network models, again, like I said before, we can use this technique in network theory of modularity maximization or identification of community. So you can see he's identified a bunch of these communities here, in total 6 communities, and then after that he basically slaps the centroids of these communities and builds a reduced order model just to track the lift coefficient. So just by tracking these community centroids and the interactions between them, which like I said, you have the same graph structure that comes from the induced velocity-based metric. Now you can use that directly to describe the lift behavior. So of course, this is showing you some training, and this is the testing. And it, based on these models, based on how these vortices pop up in the system, you can describe an observable like lift in the system. Now he's recently extended this to, again, some beautiful work in terms of using these community representations. In particular, he's identified 2 properties, which is called as the participation score and the Z-score. And what, I'm not going to go more into the details. Again, you can refer to this paper on down. What he talks about is, again, these, core structures called as connectors in the graph. Now, the connectors have really good inter-community strength. So you can imagine if I have communities in the graph, if I want to affect more of the other communities in the graph, I have to choose the flow structures that have higher interactions with the intercommunities. And those he identifies as connectors. And he shows some, beautiful, theory as well in the fundamental, vortex dynamics problem, as well as, in turbulence, to show that these connectors are really, really good in terms of flow modification because they have a larger impact over the global, system behavior. So as you can see, we started with something really, really simple, a discrete point vortex model, but then we started, scaling up to a laminar, flow system where you again use network theory, build these edges, build observable models. And then the other one is you can do flow modification. Once you identify, these community structures, you can basically say, hey, which nodes have higher inter-community strength, which can collaborate, more in some sense. If I can collaborate more, that just means I build a wider network in some sense, which means I can spread information faster. So networks really, really uses this idea, leverages the idea of interactions and using interactions in some meaningful way to either, build sparse models or, affect a global change in terms of the dynamics of the system. Okay, so that was the vertical network kind of idea. We started with that, and then we were like, okay, let's start and apply this to a turbulence flow field. Okay, now again, the premise of this problem, we started with when we were looking at network theory. There are these beautiful categorization of the different types of networks. So on the left is shown a typical highway system, and that is called as a random network. So you can see what a random network means is that a typical node has a typical number of links that it is connected to. So there's a high degree of probability that you're going to be this node here. So the number of nodes are higher here, and you're going to have a set number of interactions. So you can see this nice looking, Gaussian probability distribution curve. Now, the other network is what you see in an airline network. So for example, all of us, if you've traveled in the US, you have to pass through, a hub, which is example Atlanta, and then you pass through there and then you go to another, a smaller, place basically. So this kind of airline network is actually called as a scale-free network. Now, what is a scale-free network? A scale-free network just means that if the larger number of nodes have a lower number of links, whereas your big structures or your hubs have a high connectivity in the network in some sense, right? That's the intuition behind the scale-free network. And this was introduced by Barabasi. And what we did is we tried to see, hey, is turbulence network, what is the property of it? Is it random or is it scale-free? And what we did is, again, we use the same induced velocity-based metric on a snapshot now. So we have each grid point as a discrete vortex. We describe the interaction in the same way. We describe this nodal strength field. The nodal strength field, all it means is it's a contour of, if I'm a node, I'm going to sum up all my interaction, and all that every node, if I sum up and I plot a contour map, this is the strength field of every node in the system, right? And if I use this strength field to plot the probability distribution, what I end up with is a weighted scale-free structure in the turbulent flow field. So you end up with these hubs in turbulence, and you end up with this nice looking law, which is S is just, the probability distribution of these trends is raised to 2.7. So you may ask, okay, what is this good for? Now, one is it highlights the underlying structure of turbulence, and you can use this in some meaningful manner to maybe build LES models or, derive closures or whatnot. Of course, we have not reached that far, but, this could be a possibility. And again, it gives some insights as to how to do flow control. Okay, before I describe the intuition behind flow control, basically, we can do this for every snapshot. And of course, you get more and more if we looked at a 2D isotropic turbulence problem. And essentially what you see here is initially you start with this nice scale-free behavior. And later on, when you get these larger coherent structures forming, you lose the scale-free behavior. And essentially, I'm just showing you a gamma plot distribution that that scale-free exponent that I was showing you over a wide range of Reynolds number. What we have seen is there is a critical circulation scale over which we start seeing these bifurcating phenomenon. Okay, so something about the underlying structure we can comment on by just looking at a network perspective in turbulent flow. Now the next question, again, like I always think about in terms of modeling and control. So once you know the underlying structure, you can use these kind of resilience checks of the system. So on the left, I'm showing you a network metric called as characteristic length. And if you perturb this network in a random manner, maybe I just remove the nodes of this networks or suck out some vorticity from the system, then what happens? If you remove it randomly, nothing really happens. If you do targeted removal, you start getting big changes in your network metrics. Okay. Now there's, again, I highlight, there's some beautiful work, recent work by Qian Ye, which I'm showing you on the right, and you can refer to this paper again, where he basically uses this idea to actually show flow modifications in turbulent flow. Okay. And he identifies some critical shear layer structures as well as hubs, and shows that these random perturbations are really not useful in terms of modification of the network. But when you use this underlying network characterization, you can use that in a meaningful way to impact larger global change in your network dynamical behavior. All right, so now I'm gonna speed up the pace a little, because now that you know the background about networks, now I'm going to describe the third network that I'm interested in, which is the modal network, which is describing interactions between coherent structures or modes in the flow. Now, before we do that, the first exercise that we need to do is construct, good high resolution modal field measurements. Okay, so this is just showing you some other, complementary work that we did to build these high resolution flow measurements by using something called as phase consistent dynamic mode decomposition. So the idea is like this: we can collect data asynchronously in multiple windows, so like blue, orange, all of these different regions, and we can collect data at different times. It doesn't matter, you just collect a bunch of data. And then what we do is, what we've observed is, in dynamic mode decomposition, when you do this modal decomposition in fluid flows, there is a transformation that happens in phase, essentially, that you need to correct when you collect data asynchronously. And that's what we did. So you can see on the top, this is phase misaligned in terms of the different modal structures that you get. On the bottom is this really nicely reconstructed mode, global mode in the flow, by using this optimization strategy to construct the full global modal behavior of your flow. Okay, so the first part is, can we collect high resolution modal structures in your flow? And that's what we've demonstrated here, is you can, even if you collect data in an asynchronous manner. And you can refer to this paper here. Okay, good. So you collected data, you have some modes in the flow. Now, again, I go back to my original question. Can you represent the energy transfer or the interactions between these modal structures? Okay. And this is where we use, again, network theory, but in conjunction with data science in some sense. So what we say is, we posit that we want to track some perturbations in the flow, modal perturbations in the flow, and we want to extract a network, basically, of these interactions, a linear network, okay, at that. So, of course, these modal interactions are not linear. They are, of course, non-linear. But the idea behind a network-based representation is, can you simply describe the behavior in terms of this adjacency matrix? And what we did is, the left-hand side is just the the perturbation radius and the phase of the perturbation. We track that. And basically what we do is we collect the data, the time series of this perturbation, and we extract the network model from basically just using a simple regression based calculation. Of course, you can soup it up as much as you want using machine learning techniques, but essentially the core idea is track some time history of the perturbations in the flow and then build a network based model. Now, as you can imagine, we are building in this space of the tracking the amplitude and phase of the perturbation. So what that yields is basically your network is going to be a complex network. So every edge weight, I'm basically showing you what the network structure looks like. Every edge weight is going to have these complex interactions of sines and cosines between the modes in the flow. Okay, so you have, this is your amplitude of interaction, and this is your phase of interactions between these different modes in the flow. So now we can see that with this representation, if we can quantify this, we can really track the energy transfer between these different modal structures in the flow. And of course, I wouldn't be showing you this if this doesn't work. I'm basically, just showing you for a canonical problem that you can extract these transfer of energies between the different modes. And of course, for a simple laminar flow problem, you have the dominant mode that basically interacts the most, so it has the most amount of outgoing edges, and the higher order modes have the most number of incoming edges. So basically, this is mode number 4, this is mode number 1. So of course, the mode number 1, it has a lot of energy. It basically spreads that energy onto the other modes, right? So as a proof of concept, we can really see this networks kind of playing a role in terms of modal interactions and neatly encompassing what the flow behavior is. And of course, we have this amplitude of interactions between the modes and the phase, and this is just tracking the network model. And of course, we just show in the paper the comparison with using just a Galerichan POD based reduction. Okay. Cool. So now what is this useful for? Okay, we built the energy transfer model. The next thing that we're going to do is basically do some flow control. So we are essentially going to track these eigenvalues. So it's a linear model. We can basically do really nice, eigenvalue tracking to see which modal oscillators are the most suitable for doing flow control. Once we choose the modes that are most suitable, then we can basically perform flow control. And here I show you the baseline network, and here I show you the controlled network. And what I'm doing here is essentially taking this flow, which was living in this limit cycle, all the way down to this unstable steady state by just using the idea of wake stabilization or killing off the modal amplitudes. And what that does is it basically reduces the drag of the system by 20%. Okay. Now, the final network that I want to show you, which I'm really excited about, and this was more recent work, is this idea of what if you only have limited sensor measurements. Okay, so mapping of the interactions, if you have higher and higher Reynolds number, you have millions of degrees of freedom, it becomes really hard, as well as you don't want to map interactions with every flow field element that you have. You want to build them from limited sensor measurements. Okay, now, how we posit this question is, can we build a control law, for example, on this airfoil, which is separated? You can see this massive separation bubble here. We have a blowing suction actuator. What is the amplitude, critical amplitude of blowing that I need to have so that I can eliminate the separation bubble? But I'm not going to give you all the data. The data that I'm going to give you is going to be lift and drag. That's it. All you're going to get from me is lift and drag, and I want you to design me a control strategy that can eliminate that separation bubble. Okay. And the idea behind using this is really simple. Again, a lot of these flavors comes from time series analysis, comes from reinforcement learning, and this is a very cheap way of, if you have some sensor measurements, to do feedback control. So all you do is you take your data, you put them in a feature space, and you cluster the data. The beauty about clustering is it segments the data into these multiple different regimes. And then what I will do is I'll say, in each regime, I'm going to have a control law B, and I'm going to iterate on what these B's need to be to basically get my objective function to be minimized. That's it. Okay, so use the trajectories, cluster them, input some control, and finally do some flow control by optimization. Okay, and you can see in the paper I talked about it in more detail how you build the control law, and you can see this B is just dependent on the control amplitude and your sensor measurement, nothing else, right? You have your sensor measurement, you have your clusters that you characterize from those sensor measurements, and you have these BKs which you're going to optimize. And how are you going to optimize? You're going to optimize with whatever function that you want to minimize. Here, I want to minimize drag and the actuation input power, and I just do a simple simplex search using this, okay? And the objective is to design these BKs such that I can eliminate the separation bubble, okay? And in doing so, what we observe is we get really clean models of transition dynamics in these, in these systems. And what I mean by that is basically what you see here is a simple Markov chain where you get these transitions from these low drag states to the high drag state. So 1, 2, 3, 4, and all of this is low drag, and 9 and 10 is your high drag. And you can see the associated flow fields related to that. Now, what happens in these associated flow fields is if the vortex doesn't shed on top of the airfoil, basically what happens is the separation bubble or this vortex gets larger and larger. And as they get larger and larger, you go into this critical regime of high drag. Okay. And that happens through this switching cluster 7, basically. But if you can shed the vortex, basically you can go back to this and live in this low drag regime. So what we want to do is cut off the tie to this vortex or the state number 7. And using this procedure of cluster-based control, that is exactly what you get. You cut off the transition to cluster number 7, and then you just live in this low drag regime. So as the vortex is formed, the vortex is shed, and you live peacefully in this low drag. And what that means to these cluster probability ratios is in the low drag state, you spend a lot more time, and in the high drag states, you spend a lot less time. And this is just showing you the cluster control amplitudes. And what happens to separation? Of course, the baseline is separated and you get fully attached flow in 2D. In 3D, you do not get fully attached flow. Though you reduce the separation bubble size quite a lot, but you can get fully attached flow. But the beauty that I believe that this has uncovered is the shear layer frequencies, which are apt to do, to kind of do this flow control, they get identified automatically in this framework. And the reason why we're not getting fully attached flow is because we do not have full flow field information. All we have is sensor measurements, right? So if I can augment the sensor measurements with some, say, trailing edge data that you can get from the flow field, then basically you can improve on the accuracy of getting fully attached flow in this framework. Now we are in a bio-inspired session, so I have to talk about some bio-inspiration in some sense, where we are going. Of course, this has not much flavor of networks, but more of the bio-inspiration flavor. Now, I'm just going to quickly run through what this means is, now what we observed is we want to shed this vortex basically fast in terms of living in these low drag regimes and not having the separation bubble to grow, right? So if we want to do that, then we want to have, kind of an actuation mechanism that basically can, you can tell me, hey, I want to shed the vortex now, or I want to elongate the vortex, and it should do it. Now, insects, they basically use phase as a very nice observable to basically, achieve that in nature, okay? So by timing the way they pitch their wings, they can get some really nice information as to how to maneuver in unsteady flow environments, okay? And so what we do is we build a simple flow or phase-reduced representation of the flow physics, okay? So you can identify when does phase delay happen in the system and when does phase advance happen. And when you can do that, this is a bunch of math and this is under review. You can check this paper out, is basically, you can design what the forcing input should be just by measuring the lift in the flow. I don't need any full flow field information again. All I need is an observable. And if you can do that, you can manipulate when you shed the vortex off from the flow. So you can see the middle is just a vortex shedding, in the baseline, and you can either shed the vortex faster or you can elongate basically the time of shedding of this vortex. So just by describing, phase dynamics of the system, you can basically alter when the vortex shedding in the system takes place. And of course, I am interested in a lot of different problems. And please, ping me if you're interested in using networks or building these methodologies in terms of more complicated flow physics. I'm interested in multi-physics problems, closure. I alluded to invariant-based characterizations, and of course, more on building the intuition in terms of network theory as well, like network controllability, observability. So there's a lot of concepts that we can leverage from network theory, as well as using this insights from fluid flows that we can leverage. Of course, this work would not be possible if I didn't have my 3 pillars of support, which is Sam, Steve, and Bing. They have supported me throughout my career, and and I wouldn't be able to do all of this work. And also, I have a lot of other collaborators, like I mentioned, Murli, Chian, Eureka, Bernd Noack, and of course, support from Army Research Office, Air Force Research Lab, and computational resources from DoD. And with that, I am open to taking questions. Hope you got something, learned something, and hope this is useful. Thank you.
Thank you very much for this really, really nice overview and inspiring overview about applications or vertical networks, turbulence networks, and to fluid flows application. Really, really interesting. So let's see. So if anyone have any question, can switch on microphone and put their question. So, Disha, yeah, if you have.
So, terrific presentation, really like it. So, I get to know this network theory the first time I met with Giovanni, and then start to book to the network the seminars. I really like how slow and also concrete the presentation you have to talk about the background, to guide us through. But I guess I have missed something. So in the vortex network. So what's, for example, in page 11? So so a conical von Karman vortex tree. So how do you first identify these vortex? So which means that the node. So I mean, the definition of vortex is debatable, right? So how did you find these nodes to begin with?
Beautiful question. So basically, we used the same idea that is here. So in some sense, we started with this discrete point vortices, right? Now, this is a Lagrangian idea, right? So you have these vortices that are moving in space, and everything is, exactly in the definition of, the Biot-Savat's law and the dynamics and all of that. Now, this is a Lagrangian framework. Now, when you go to laminar or these canonical problems and even turbulence, right, which I describe later on, like you said, you can use a lambda criterion and Q criterion and all of that to define these vortices. But essentially, we did none of that. What we did is we said every grid point in your simulation has an associated vorticity, right? So what you can do is you can build time varying networks, basically. So every grid point is a node now of your graph, and every grid point in your in your system has an associated vorticity associated vorticity value. We just use that associated vorticity value as the strength. So if you go back to this definition here, the associated vorticity value is going to be your strength, and the distance now between your grid points, which is fixed because you have a grid. It can be structured, it can be unstructured. the way you have your computational domain, you can use that and define these distances, right? So once you can define this in 2D and of course this in 3D, then you can define basically just the dense interaction between all-to-all grid points in your system, right? So if you have, say, n grid points in your system, you almost have these n squared type of interactions. Every grid point is interacting with every other grid points in your system, right? So basically you can have that. And then what he's done here is he's basically taken that network, that dense network, you slap it into this modularity maximization, and it automatically identifies these core structures in your network and says, hey, this structure is here, this structure is here. There are these 6 structures that should be there in your network. Give me that. And then, of course, the centroid is more like, if you want to build a reduced order model, instead of taking this entire piece of vortex, basically, we don't know, we exactly never use the methodology of a vortex or a coherent structure. We always call it a community, just to be on a safe side, because of the exact fact that these things are debatable in literature. But these structures, these community structures, are something that we can extract really nicely from this formulation.
Beautiful answers. So just a very small question on the same section in the page 7. In terms of like when you constructing the weight, the alpha is some parameters, I guess, you can tune or play with.
Yes, that is correct. So beautiful question again. So let me just I don't know what your question is, but let me have a the reason why we have that alpha is to, initially, the graph theoretic methods were all based on symmetric, undirected configurations. There's a lot of literature on that. So we explicitly, initially, when we were starting to play with this, we symmetrized the graph. But recently, I want to say there's a lot of improvements on doing directed, graph algorithms. And there's a lot of drive towards that. So you don't need this explicit symmetrization in terms of alpha. So you can just take your weights and run with it, basically, whatever form they are in. Of course, that would add, this directedness, or would add the signed graphs idea. So we need to have algorithms that are capable of handling directed, weighted, signed graphs. If you can get there, if whatever you want to do can, there's graph theoretic methods, or you want to build graph theoretic methods that can do that, then you don't need this explicit symmetrization of your adjacency matrix.
Yeah, you answer like beforehand and all the things that I want to know.
I get that a lot because the thing is, the alpha is something that initially it was again something that we didn't want to have in the model, because if you symmetrize it, you lose a lot of these ties. But that was just to, at that time, which is I'm talking as if I'm like very, very old, but this is just 5 years old work. But in some sense, there is a lot of algorithms out there already in undirected graphs, which we wanted to leverage. So that's why we symmetrized it. So, yeah.
Thank you so much. So I have one more question, but how about I'll leave this to the floor to see whether there other people have questions. If not, then I'll ask that like accordingly. So, Giovanni?
I think there is no more question. I have one question, but of course I can put this at the very end. I cannot see any other hand raised, so I think we can continue this show.
Okay, so allow me to continue. So in page 25, in 25, which when you talk about the flow control of the foil, especially when the sensor is very, very sparse, very, very limited. For me, an experimentalist, that's like a great, interesting news. But one question I guess I have is that, for example, when you try to clustering the whole data, do you?
Yeah. So this is a very.
What's the window size you pick for the CLCD?
Very good point. So what I do is basically you have your baseline flow. So if you're running an experiment, you would basically run your experiment and then collect a lot of just the baseline data. So all I need to cluster is you would not force the system. You would just run the sensor measurement over whatever you can. So if you have a long time series of this data, you collect that time series. If you don't have the time series, then you basically, you need, of course, I have to say, you need whatever your observable is, you need time series data for that. But I don't need any forced data or anything of that order. You give me baseline data of your unforced system, that time series is all I'm using to cluster the data. So you run this experiment, you collect the sensor data over however long you have, then just slap it onto this feature space, build the clusters. Once you build the clusters, you're done. You don't need to like recluster or do anything. Of course, reclustering, some of the drives in my group is to think about reclustering and think about these adaptive algorithms to enable this. But essentially, here all I use is baseline data and then use that to cluster and then use that to control, basically. So whatever time series, unforced time series you have, you just cluster that and then build on these cluster-based representation. The S that I was talking about, when you do the control, you just measure the same feature space. That's all I mean by that. The cluster association automatically comes from this radial basis function that I impose here, because you already have the baseline clusters, and this difference is going to take care of what your cluster association is from the baseline. So you don't need to add more clusters or anything like that once you have your baseline data.
Yeah, I have follow-up question, but let me read the paper and send you in email. And I see other people have.
Sounds good.
Yeah, we have time for another question by Chica.
Go ahead, Chica.
Okay, hello everyone. My name is Chika, and I'm happy to join you from Hong Kong. So my question is on the intensity. I saw when Dr. Nair talked about the intensity of a vortex generator. So I wanted to know if Dr. Nair, whether you considered a relationship perhaps between these vortex intensity and a physical phenomenon like the swelling flows, perhaps the intensity of fluid swelling flows.
Very excellent question, Chica. So
yeah.
So the thing is, I don't have a very good answer for you because I am not an expert, but hopefully soon in a year or two, you might have something, because I am interested currently in swelling flows.
Okay.
I'm thinking about it in terms of swirl numbers and all of that. So these swirling flows are interesting, right? Because they have these vortex rings kind of structures that you can get. And these vortex rings, their intensity, of course, you have they decay over space, and it's a very rich problem again. Now, to be honest with you, I don't know how to comment on it right now, but that's an excellent question. I think that is definitely a work for the future to think about, instead of thinking about these core vertical structures, maybe think about these vortex ring type of representations that can incorporate these intensity and swirl based elements into the interaction. But very, very interesting question. Yeah, I don't have a good answer for you, but
no problem. Thank you so much.
Yeah.
Thank you so much. Yeah.
Thanks.
Okay, thanks. So we have time for a quick question. One more question.
Hello, Aditya. Chandan here.
Chandan.
You hear me? Yes. So my question was like, it was very intriguing talk. So my question was like, how much is this network theory applicable for unpredictable flow situation? Let's say we have a chaotic flow past an airfoil where like every interaction changes and towards the transition to turbulence. So how the adjacency matrices and this weightage changes in your formulation?
Again,
could you elaborate that?
No, that's a beautiful question. So this is again something that that is very interesting, and I know Giovanni has explored this a little bit. But thinking about precursors or network properties. For example, if I just show you this graph, this shows you a property of a network, right? It's a scale-free distribution. And then I showed you here that you start getting these bifurcations at a critical circulation scale. Now, what network can help you with is probably determining these precursors to the events that will take place. So for example, because vertical interactions are so fundamental, right, in some sense, that you don't, that if I posit that the interactions between I and J is X, then over a period of time, that X interaction could lead to a particular physical phenomenon. So there's physical phenomenon is almost, a net effect of the interactions and not the other way around. So I believe that, the interaction is more fundamental in terms of characterizing it. And what networks can help you with is identifying precursors. For example, if you had, like you mentioned before, a chaotic system, if you have bifurcations, or if you have lobe switching, or if you have intermittency, or any of these phenomenon, extreme events, you call it basically. What I believe network can do, and of course I don't have results for you showing that, but I believe that network can identify some precursors to what can lead to these events taking place in the flow. And if we can do that, that's, I would say, a big win, because you're identifying these precursors from fundamental interactions rather than just looking at a flow observable, right? Because a flow observable, you may not have the sensitivity to gauge that this particular interaction down in the line is going to lead to this. And again, these are not the only networks out there. There are other networks called as recurrence networks, which are also amazing at identifying these behaviors. So you have these recurrence phenomenon that happen, and when the recurrence happen, maybe you have something leading to an extreme event. So
yeah, so that was my follow-up question actually. So this particular network-based approach that you have presented, how is it related or superior to the recurrence network-based approach?
I wouldn't. I never like to talk about superiority and stuff in terms of networks, because it's a purely design problem, right? Because it's, the way I think about it is, what is your input and what is your output, right? And if you have the particular things that I talked about are for a particular set of inputs, for example, vortices, if you have measurements or you have some sensor measurements, then what is the best model that you can get and the best strategy that you can posit. Now, in your case, or in the case that you were thinking about in terms of recurrence network, they may be a much better model in terms of modeling the input-output characteristics that you care about. For example, an extreme event, I believe that a time series, time delay-based approaches, or recurrence-based approaches are much more suited to identifying these extreme events or transitions. So if you can formulate your problem in that context as an input-output, I believe that you can uncover some of the fundamental interactions that lead to that. So
yes, but I would say that your approach is more suitable in terms of identifying the interactions between the physical vortices, which we cannot do through recurrence properties. So yeah, that's what it's beautiful. But I will look forward to your future works to know like how it can be applied to unpredictable flows like higher order chaos or turbulence. Thanks a lot.
Very good question, Chandan. Yes, cool.
Okay, good. So thank you for again Nair. I think we are done, and thank you everyone for joining this talk. And yeah, thanks again to everyone and Dr. Nair for this beautiful work, and we look forward to your future works. Yeah.
Thank you. Appreciate
Thanks.
it. Much. Stay safe, stay healthy. So.
Yep.
Okay.
Bye.
Bye-bye.
Bye. Bye.